CMOS transmission gates, pass gates. In this session, we will examine a simple switch circuit called the CMOS transmission gate (TG) or pass gate, and present a new class of logic circuits which use the TGs as their basic building blocks. As shown in figure, the CMOS transmission gate consists of one NMOS and one PMOS transistor connected in parallel. The gate voltages applied to these two transistors are also set to be complementary signals. As such, the CMOS TG operates as a bidirectional switch between the nodes A and B, which is controlled by signal C. If the control signal C is logic high, that is equal to VDD, then both transistors are turned on and provide a low resistance current path between the nodes A and B. If as you can see in this figure, the four different representations of the CMOS transmission gate. As you can see in this figure, bias conditions and operating regions of the CMOS transmission gate shown as functions of output voltage. On the other hand, the control signal C is low. When both transistors will be off, the path between the nodes A and B will be an open circuit. The condition is called the high impedance state. Note that the substrate terminal of the NMOS transistors is connected to ground and the substrate terminal of the PMOS transistor is connected to VDD. Thus, we must take into account the substrate bias effect for both transistors depending on the bias conditions. Figure also shows three other commonly used symbolic representations of the CMOS transmission gate. For a detailed DC analysis of the CMOS transmission gate, we will consider the following bias condition shown in figure. The input node A is connected to a constant logic high voltage Vin equal to VDD. The control signal is also logic high, thus ensuring that both transistors are turned on. The output node B may be connected to a capacitor, which represents capacitive loading of the subsequent logic stages driven by the transmission gate. We will now investigate the input-output current voltage relationship of the CMOS TG as a function of the output voltage Vout. It can be seen from figure that the drain to source and the gate to source voltages of the NMOS transistors are VDSN is equal to VDD minus Vout, VGSN equal to VDD minus Vout. Thus, the NMOS transistor will be turned off for Vout greater than VDD minus VTN and will operate in the saturation mode for Vout less than VDD minus VTN. The VDN and VGS voltages of the PMOS transistors are VDSP equal to Vout minus VDD, VGSP equal to minus VDD. Consequently, the PMOS transistor is in saturation for Vout less than mod VT VTP and it operates in the linear region for Vout greater than V mod VTP. Note that unlike the NMOS transistor, the PMOS transistor remains turned on regardless of the output or regardless of the output voltage level Vout. The analysis has shown that we can identify 3 operating regions for the CMOS transmission gate depending on the output voltage level. These operating regions are depicted in figure as shown as functions of Vout. The total current flowing through the transition gate is the sum of the NMOS drain current and the PMOS drain current. ID equal to IDSN plus ISDP. At this point, we may devise an equivalent resistance for each transistor in this structure as follows: R equal N equal to VDD minus Vout by IDSN. R equal P is equal to VDD minus Vout by ISDP. The total equivalent resistance of CMOS TG will be the parallel equivalent of these two resistances. R equal N equal R equal N and R equal P. Now we will calculate the equivalent resistance values for 3 operating regions of the transmission gate. Region 1. Region 1. Here the output voltage is smaller and than the absolute value of PMOS transistor threshold voltage, that is Vout less than mod VTP. According to figure, both transistors are in saturation. We obtain the equivalent resistance of both devices as R equal N is equals to 2 VDD minus Vout by K and VDD minus Vout minus VTN whole square. V equal P equal to 2 VDD minus Vout by KP VDD minus mod VTP whole square. Note that the source to substrate voltage of the NMOS transistor is equal to output voltage Vout, while the source to substrate voltage of the PMOS transistor is equal to 0. Thus, we have to take into account the substrate bias effect for the NMOS transistor in our calculations. Region 2. In this region, mod VTP less than Vout is equal less than VDD minus VTN. As the PMOS transistor now operates in the linear region, while the NMOS transistor continues to operate in the saturation. V equal N equal to 2 VDD minus Vout by K and VDD minus Vout minus VTN whole square. V equal P is equals to 2 VDD minus K out V out KP 2 VDD minus mod VTP VDD minus Vout minus VDD minus Vout whole square is equal to by KP 2 VDD minus mod VTP minus VDD minus Vout. Region 3. Here the output voltages is Vout greater than VDD minus VT and consequently the NMOS transistors will be turned off, which results in an open circuit equivalent. The PMOS transistor will continue to operate in the linear region. R equal P equal to by KP 2 VDD minus mod VTP minus 2 VDD minus Vout. Combining the equivalent resistance values found for the three operating regions, we can now plot the total resistance of the CMOS transmission gate as a function of the output voltage Vout as shown in figure. Equivalent resistance of CMOS transmission gate plotted as a function of the output voltage. Here you can see in this figure replacing the CMOS TG with its resistor equivalent for transient analysis. It can be seen that the total equivalent resistance of the TG remains relatively constant, that its value is almost independent of the output voltage, whereas the individual equivalent resistances of both the NMOS and the PMOS transistors are strongly dependent on Vout. This property of the CMOS TG is naturally quite desirable. A CMOS pass gate which is turned on by a logic high control signal can be replaced by its simple equivalent resistance for the dynamic analysis as shown in figure. The implementation of CMOS transmission gates in logic circuit design usually results in compact circuit structures which may even require a smaller number of transistors than their standard CMOS counterparts. Note that the control signal and its complement must be available simultaneously for TG applications. Figure shows a 2-input multiplexer mask circuit consisting of 2 CMOS transmission gates. The operation of the multiplexer can be understood quite easily. If the control input S is logic high, the bottom TG will conduct and the output will be equal to the input B. If the control signal is low, the bottom TG will be turned off and the top TG will connect the input A to the output node. Figure shows an 8 transistor implementation of the logic XOR function using 2 CMOS TGs and 2 CMOS inverters. The same function can also be implemented using only 6 transistors as shown in figure. Using the generalized multiplexer approach, each Boolean function can be realized with a TG logic circuit. As an example, figure A shows the TG logic implementation of a 3-variable Boolean function. Note that the 3 input variables and their inverses must be used to control the CMOS transmission gates. Figure 2-input multiplexer circuit implemented using 2 CMOS TGs. Figure 8 transistor CMOS TG implementation of the XOR function. Figure 6 transistor CMOS TG implementation of the XOR function. Figure A CMOS TG realization of the 3-variable Boolean function. B. All CMOS transistors can be placed into one N well to save area. Including the 3 inverters not shown here, the TG implementation requires a total of 14 transistors. An important point in TG logic design is the conducting TG network. Low implementation paths should always be provided between the output node and one of the inputs for all possible input combinations. Is to make sure that the output node with its capacitive load is never left in a high impedance state. Here you can see in this figure mask layout of the CMOS TG circuit shown in figure. If each CMOS transmission gate in TG logic circuits is realized with a full NMOS and PMOS pair, the disjoint N-well structures of PMOS transistors and the diffusion contacts may cause a significant overall area increase. In an attempt to reduce the silicon area occupied by the TG circuits, the transmission gates can be laid out as separation NMOS and PMOS pairs with all PMOS transistors placed in one single N-well as well in figure B. However, the routing area required for connecting the P-type diffusion regions to input signals must be carefully considered. The layout of the TG circuit is given in figure. Thank you.